Okay, guys, mass spec. Any questions about mass spec? There's a new handout, or maybe today, but definitely tomorrow. Any questions about mass spec?
Explain how to read it.
No questions about mass spec?
What is this?
What is it? Mass spectrometry. Determines the mass of a compound. IR tells us the bonds. Well, you deal with bonds, but IR ultimately tells us functional groups that are present. IR doesn't tell us anything about the mass of the compound. It could be a saturated alcohol with 4 carbons, or it could have 12 carbons. Mass spectrometry, first off, it's not mass spectroscopy. We don't use light. Very often it's called a type of spectroscopy, but we actually do not use light. It's called mass spectrometry. Here's a little bit. They're using it in medicine to detect cancer from some type of biomolecules that occur in cancer. We talked about the IRs. It's hard to tell these apart. Mass spec would easily tell these apart. There's a mass spec of each compound there. You can go back and look at that. Let's start here with how the method, how mass spec takes place. How do you get the mass? Start with a molecule, of course. Down here comes the system. This is all in a box. But on the outside of the box, you can have something where you can inject a sample. Typically, the sample is prepared by dissolving your compound in a solvent. You inject it in, and it goes through the mass spectrum. What does it do? It first encounters some type of ionization method. You got to ionize your molecule. There's many types of ionization methods. A newer method won Nobel Prize about 10, 15 years ago. Been doing this for 50 years. Most common method, kind of the simplest method, is electron beam, also known as electricity. If you zap a compound with electricity, electrons in, it will cause the molecule to lose an electron. It will cause the molecule to ionize. X-rays will also cause the molecule to ionize. That's why X-rays can be dangerous. But here we're using electricity. Ionize, the molecule loses an electron. So this and the electron is shot out. It goes somewhere else. But now that it's lost an electron, what's its charge? Positive. So it's now an ion. But it's also a radical. Because we assume that the molecule, all electrons are paired. Every molecule we've seen in this class, electrons have been paired. Well, not all. We did that radical reaction to the alkyne. If you look at any of the drugs and any of the sheets, it's all paired electrons, either a lone pair or a bonding pair. Well, if you lose one electron, that means there's one electron left behind that's not paired. So it's being shown here to indicate that what you form here upon ionization is a radical cation. Sometimes that's just denoted as M+, but please note that it is a radical. Single electron. Also known as the molecular ion, because this is really the molecule, but it's now an ion. This has the same mass as this, so the electron mass is negligible. This we can observe the mass of. This is called electron impact. You can only observe the mass of ions, and in particularly positive ions known as cations. We'll look at how we observe the mass down here. One thing that we will see is that the molecular ion is prone to undergoing fragmentation, breaking apart, decomposing into other fragments. The molecular ion, the radical cation, when it cleaves, will form a radical and a cation, typically. The cation fragments can be observed because they're charged. Neutral radicals are not observed. You only observe charged species. Fragmentation is often predictable, and we'll learn how to predict. Based on what we predict, we can interpret a spectrum. Just like when we do IR, we know how to predict peaks from structure. Why do cations give peaks? Well, the system is down here. Here we go. We inject, usually with a syringe. It encounters an electron beam. Ionization takes place, and we form the molecular ion. Now that it's an ion, it's charged. Well, down here on this end, there's a magnet. And the ions are pulled towards the magnet. But only the positive ions. Only the positive ions are pulled towards the magnet. But when they get to the magnet and they encounter the magnetic field, they're deflected. But the degree of deflection is based on the mass. The heavier the ion, the less it's going to be deflected because it contains more momentum and everything. So the magnetic field will have less effect on it. So a heavy ion comes through and it barely is deflected. A lighter ion comes through, encounters the field, and it's deflected much more. But the degree of deflection is basically correlates with the mass. And that actually can be plotted. And you can see, whenever you look at a mass spectrum, what you're really looking at is how much everything was deflected. But that's essentially mass, because it relates to that. And we can plot that. That's how you ultimately get what we call a mass spectrum. But along the way, there's different ions that can hit here. The original molecular ion could make it all the way through and hit here, and you would get a mass for that. But along the way, fragmentation can also occur, and you can see these fragments, how much they were deflected. And so you end up with many peaks, not just the molecular ion peak. Mike?
So what keeps it from losing 2 electrons, I guess? Is it just probability in there? Because if it had a negative or +2 charge, it would deflect twice as much.
Okay. You've been doing some reading?
Yeah.
Okay. Regardless. Whatever you do, don't read before you come to lecture, right? No, it's a good question. That's why we have M to Z ratio. Usually when we do mass spec, we assume that everything has a +1 charge. If it has a +2 charge, it's going to be deflected twice as much, even though the mass has not changed. That is very critical. What we actually plot is not mass, but we can refer back to over here. It doesn't say it on the x-axis, not on those. It does on the next page. Down here, these numbers are actually mass to charge. M to Z ratio, mass to charge. Okay. This whatever this is right here, this species that gave a signal at 71 has a mass to charge ratio of 71. Now, if the charge is 1, the mass is 71. Let's do a whole number. 40. If the charge is 1, the mass is 40. What if the charge is 2? The mass is really 80. This is the ratio. The ratio is 40. Right? It's either 40 to 1 if the charge is 1, but if the charge is 2, what's this number going to be? 80. Okay? And so you do have to be careful. This could be a species that has charge a mass of 80, but it also has charge of plus 2. In the end, we're going to assume that all charges are plus 1, and in the end, I'm going to assume that all M to Z's are really your molecular weights. That is, the molecular weight is really 40 and not some multiple of it. Okay. Good question. You could have diions, you could have trications, and when you get to big molecules like proteins, that becomes much more important because they have propensity to really become lots of charges. Other questions?
So is it just sitting there until it actually gets, like, will it not accelerate until it gets the charge put on it as well? Is that
Yeah.
like there's in the
Yeah, it needs to be ionized first to be accelerated and deflected. Lucy?
What's the question mark on it?
What's the what word?
The question mark on the first half of the graph? Further down, on the graph.
Right here?
Yeah.
Let's wait till we get there. Yeah, we'll interpret and we'll see what the question mark was. Okay, so here's an example down here, molecule. Let's say you start with this ether here, phenylethyl ether. You do electron impact, you ionize it. This is typically show, okay, where's the single electron? Here you typically do not, sometimes you can. I just show that it's a radical and it's an ion. So with a bracket over here. This is a radical cation. It's formed by ionization. This has a mass of 122. Add it up, 122. This may make it through the system, be deflected, hit the detector, and give you a peak at 122. Or it can fragment. Different types of fragmentations, we'll call some of them alpha cleavage. It can fragment, basically it will cleave. I'm showing where it cleaves between that carbon and that carbon. When a radical cation cleaves, what does it form? A radical and a cation. Radical cation cleave to give that radical and this cation. We'll learn how to do that. Guess what? We're going to make cations that are the best. That's the ones you're going to form. And what's the best type of cation? Carbocation we're dealing with here. Tertiary, but what's a better way to have a better cation? Starts with a re or red.
Resonance.
Resonance, yeah. Resonance stabilized. We'll be looking for resonance stabilized cations. That's why mass spec goes so good with resonance. That's a resonance stabilized cation. Long pair, boom. Resonance stabilized by the long pair. That's a great cation to form. That has a mass of 107. There's tricks to figure out that's 107 because that's 15. 12 and 3 is 15. So what's 122 minus 15? 107. So you quickly be able to see your numbers. Which species gives a peak in the mass spec? Only the ions. You'll never observe that in the mass spec. Okay? So your mass spectrum here, you would expect to see a peak at 122, 107. You'll probably see many other peaks. Because there's other ways for it to cleave. We will predict the best way to cleave. Just like in IR, you see lots of other peaks that we usually don't assign, mostly in the fingerprint. You'll see lots of peaks we don't assign in mass spec also. But we will get the information we want. Okay, we're going to go through this like I did with the IR. We'll look at different types of compounds, their mass spectrum, and interpret. First compound shown up top is, what's that, hexane? Just a plain hydrocarbon. Molecular weight is 86. It's C6H14. Carbon is 12, H is 1. Why 86 is a whole number. Why not 86.0093?
Because that's the average.
No, it's not an average. Well, even the 0093 is an average. Basically, why am I doing whole number and not like 3 or 4 decimal places?
It's hard to show, because it's hard to see.
The actual mass is.
Because there's 2 types of mass spec. There's typical. We call this low res, low resolution. Harder to measure the deflection 2 to 3 decimal places. It's easier to whole number. Your basic mass spec is just whole number mass. If you want to get 3 or 4 decimal places for your fragments, that's called high res mass spec. Okay? I may mention that a little bit later. That's where you get like 4 decimal places. But that's a much more expensive instrument. Okay? So we're doing just low res mass spec with whole numbers. So you can add it up. 12 carbons is, 6 carbons is what, 72? And then 14 H's is 14 because they're 1 apiece. We're total of 86. Okay, this is a mass spectrum. First off, molecular ion. It does appear here 86, 586. So that's a molecular ion. Note that it is a radical, and a lot of times people do not show the dot there, the radical part. But your molecular ion is always a radical, yeah? So apparently it made it through the system and hit the detector and gave a peak at 86. But a lot of other stuff hit the detector with other masses. How can this compound cleave? We're going to cleave by breaking bonds. Now, I showed this here, 1, 2, 3, 4. We'll lower this down a little bit. That's where the radical cation, okay, I'm not going to show the plus here, but it has to first form that. Then it cleaved here to give that. And if it gave that, what's the other fragment that was formed? A 2 carbon, and that being radical. So if the molecule ruptured there, cleaved there, we get these 2 species. That's not observed, it's not charged. This is observed. What's its mass? Well, you just add it up. How many carbons? C4, that's 48. How many H's here? 3, 2, 2. How many on the N carbon? 2. So what's that? 9? 48, 9 is what? 57. Is that 57? I can't see it. 57? I bet it is, yeah? Okay. So that's one way it cleaved. Apparently it cleaved another way. 3 carbon fragment. Give that plus a 3 carbon radical. But that's going to be what? 36 and 2, 4 and 7. 43? Is that 43? Yeah. Hold on. Yeah, minus 43. Was the original 86? Okay, that's like half. Terminology, or just sort of ways to do this. That peak is at 57, yeah? So just seeing it is at 57, how much has it lost from 86? 29. That's why I say that this is an 8 plus minus 29 peak. You often state what a peak is by saying what was lost to form it. And guess what? 29 is always, usually, an ethyl. Right. 2 carbons and 5 H's. So when you see something loose in 15, that's always a methyl. 29 is always an ethyl. A propyl fragment is always 43. So you can see, hey, it lost 43, it must have lost a propyl. So you kind of get used to certain numbers. What is this down here? Apparently, I don't know what it is. How much is it lost? This is M minus what? Well, that's 29, so be 57, right? M minus 57? It lost 57. How could it lose 57? Well, 29. Or maybe I do know what it is and I wanted you to tell me. I can't remember what the question was.
It's the eyeball.
I mean, 29 it would be maybe what? Okay, this is what I want. What is it? Here's the question. Show the complete structure for 29. What is 29? Got it, Robert? Ethyl what? It's not an ethyl radical. I mean, a plain ethyl radical will not give a peak. What is it?
Okay.
It's an ethyl cation. Right? I mean, this does not give a peak. It has to be charged to give a peak. Apparently, this is where it cleaved. It also cleaved a 4 and a 2, but it cleaved, when it cleaved, it left the cation on the 2 and made the 4 the radical part. In the end, with a molecule like hexane, when there's no resonance possible, you're not going to get any predicted cleavage, really. It's going to cleave all types of places. And I tried to interpret some. You thus have lots of peaks. But the one below, look how fewer peaks you have. You actually have just one significant peak. First off, your tallest peak in your mass spectrum, see over here, this is just relative percentage. Your tallest peak is always set to 100%. Everything else is just relative to that. This is 20% of your tallest peak. Your tallest peak is called what? The base peak. So here the base peak is at what? 50, is it 57? 57? That means that the molecule overwhelmingly wanted to cleave to give that cation. Somebody tell me why that cation was so favorable. Because it's tertiary. Okay? Your best cation is going to form. So where did it cleave? Molecular ion cleaved here to give, is that it there? To give that cation plus that radical. Make sure you don't add carbons. That's 4 carbons there, and that's 1, 2, 3, that's 4 there. But this guy is going to be observed, nice tertiary cation. And so that's where we actually predict to get a cation, by cleavage. So this molecule is more of a predictable cleavage. Uh, 114, did we see the molecular ion? Yeah, I think we looked. The fact that 114 is not shown, I would say that means there's nothing there. The molecular ion does not always have to be seen. Once it ionizes, the original molecule, molecular ion, has to make it through the system, be deflected, and hit the detector. But what if it breaks apart instantaneous? It's never going to make it to the detector. What type of scenario, why would something break apart instantaneous and something else not? Well, if it's very favorable. If this thing is very favorable to break apart, it's going to do it real quick. Apparently this is very favorable. Why very favorable? Because it broke apart and formed a tertiary cation. Very easy to form. You will not always see the molecular ion. 90% of the time you will. But it doesn't have to be there. It could break apart.
So these are for specific molecules then, each group. So if you had one that contained isotopes, it would be either to the left or to the right of them. There, and there would be a little bit of a,
We will see isotope patterns, yes, a little bit later. Let's take a look at isotopes. Here we go. Here's a compound with bromine in it. It says the mass of the molecular ion is 122. Well, they're only telling you half the story. It's also 124. What do we know about bromine? Bromine has two major isotopes, 179 and 181. What's the ratio of the two? It's about 50-50. In any sample of this compound, half the molecules are going to be something 79, and the other half are going to be something 81. That adds up to two different masses, 122 and 124. It's like you got two types of compounds in there, some with 122 and some with 124. If you do the mass spec of this mixture, 50-50 mixture, you expect two different molecular ions. And here you go, 122 and 124. This would be called M+, and this is often called M, often the plus is not said twice, M+2. But it's really an M+ radical +2. We call that an isotope pattern for bromine. Why is it a pattern? Because the ratio is 50-50, thus your peak height is approximately 50-50. Because there's an equal amount of each in there. So you get two molecular ion peaks in a +2 ratio, or +2 pattern. But then the molecule can also cleave. Instead of predicting, let's see what we got over here. I've got a base peak at, what is that, 43? I bet it is. 41, 2, 3. Is that 43? Yeah. Okay, what's 43? Typically a propyl. 15, 29, 43 for your alkyls. But this is that plus what? What else was formed when that cleaved? What's the BR? Radical. Yes. So the radical cation cleaves to give a radical on a cation. So it cleaved to produce BR radicals. BR radicals, by the way, if we had looked at that mechanism with peroxide, Aaron, we would have seen BR radicals. Okay. Apparently it wanted to cleave predominantly that way and give that cation. The other peaks are minor. We may or may not try to interpret these. Okay. Ultimately, we'll see what we need to do. Down below, we have an example of chlorine. Chlorine has two major isotopes. (35 and 37). What's their ratio? 3-to-1. Not 1-to-1, but 3-to-1. So one is 75% and one's 25%. And so with your molecular ions, you don't expect a sort of a 1-to-1 ratio. You get this 3-to-1 ratio. Because the one with 35, which adds up to 78, is 3 times the one with 37, which adds up to 80. So 3-to-1 is your chlorine ratio. Bromine and chlorine are your two halogens that have isotope patterns. Fluorine does not have a natural isotope. Fluorine is all 19. Fluorine 18 is not natural, it's man-made. And what do we do with fluorine 18? It's
radioactive, it's man-made, but what do we do with it? They actually make it over on Central Avenue. What do we do, what do we use it for? PET imaging in the hospital. Anybody heard of PET imaging? Positron emitting topography. F-18 is a positron emitter. It decays by emitting a positron. The positron can be used in the body to give an image. So we use F-18 for that, but it's not natural. Only F-19 is natural, so it's 100% abundant naturally. Iodine also, there's no concern with isotopes. Just chlorine and bromine for your halogens. You also see isotopes with many other things like sulfur, tellurium. We made some tellurium compounds a while back. Many major isotopes. When you do the mass spec, your molecular ion, you see like 6 peaks. Well, there's 6 different isotopes. For us, chlorine and bromine are your 2 main ones. There are other peaks here. I kind of tried to assign these. Look right here. What does this 3-to-1 ratio look like? It looks like an isotope pattern. Just like that. That means that whatever this is has chlorine in it. Because even when it cleaves, your cleavage product still has either chlorine 35 or 37. Where, look over here, whatever this is, does it have chlorine? Well, there's 2 reasons I know it don't have chlorine. First off, it's only 27 and chlorine's at least 35. But if it had chlorine in it, right here, does that have chlorine in it? How do you know that doesn't have chlorine?
There should be another.
Because we should expect an isotope peak, a twin, that is a third the size. Because one would be chlorine 35 and then you would have chlorine 37. Okay? Do you understand how you can tell that, hey, that fragment has your halogen in it because I see the isotope pattern in the fragment? Okay.
So the gas chromatography thing won't separate the isotopes? Is that?
It may. It may. I haven't talked about GC. I mean, GC may separate, but if you don't hook the mass spec up to GC, then it's all just still a mixture, and it's all coming through at the same time.
In that case, we would get all the impurities in there too. We would be able to distinguish.
Oh, yeah. It's going to give you masses of whatever's in your sample. If it's impure, you're going to get masses of that. That's why mass spec is usually hooked up to GC. And GC first separates things, and then you get a mass of each individual component. It makes interpretation a lot easier. Something we need to say over here. What's the mass of bromine? What's the mass of bromine? If you look at the periodic table, if you got a compound with bromine, you add it up molecular weight, what number do you use for bromine? 79 point what?
9.
Why 79.9 and not 79?
Because it's in between.
It's 79.9? Let me check my periodic table. 79.9, bromine. Why not 79 or 81? Because the periodic table is an average of your isotopes, a 3-to-1 average. If you 3-to-1, 79 and 81, and average them together, what do you get? 79.9. That's because in any bulk sample, you have 3-to-1 ratio of 78 and 81. No, 78 and
It should be a
It's
one,
a-
right?
It's a
79 and 81, and I'm talking bromine, so it's 1-to-1. Neither one of those bromines are 79.9. That's the average that's in your bulk sample. In mass spec, we don't see an average. We see individual atoms and molecules. So we either see the 79 or the 81. And you actually get two different peaks. Okay, let's look at other functional groups and let's get to some that's more predictable. Here we have an ether. Molecular weight is 74. Add it up. So the molecular ion would be 74. Do we see a 74? Yeah. So there's your molecular ion. We got a peak at 75. What is that?
Carbon
Carbon what?
13.
Who said that? Yes, tell me more. Why carbon 13?
1%.
Yeah, because on day one I told you the percent of carbons, 99 are carbon 12, and what percent is carbon 13? Yeah, 1% of the carbons in your body are C13. 1% of the carbons in that molecule are C13. Okay? And the molecule as a whole. What's the chance of there being a C13 in that actual molecule? It's probably also 1%. I'd have to do the math. Is that right? Okay. That's where one of the carbons is C13. You got a molecule where it's C12, 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 and then one of them is a C13. Well, that's going to add up to a mass of 1 greater. That's an isotope pattern for carbon. But usually it's ignored because it's so small. We only talk about significant isotope patterns like the bromine and chlorine. Why don't we see a 76? Because it's highly unlikely to have two C13s in the same molecule when only 1% of all the carbons are C13. But I guarantee you, there's probably some out there. It's just so little that it doesn't show up in the detector because of the sensitivity. Okay? So what do we get here? I interpreted this as, first off, I saw that it's 74 to 59, so it lost what? That's M minus 15. Now that all I know it lost 15, it lost probably what? A methyl. Now, where is it going to lose a methyl? Well, there's really only one place to lose a methyl, it's on the end. Other examples, we may have choices. But it's going to cleave here to give that plus what? CH3 radical. We don't see that, we just see this. Now we really didn't have an alternative, but why is this a good cation? Because it's resonance stabilized. And that's what we would predict. We're always going to predict our resonance stabilized cations. Where are the resonance stabilized cations going to occur? Well, this is where they're going to occur. They're going to occur on an atom next to a lone pair. Because if it occurs on an atom next to a lone pair, what can you then show? It's resonance stabilized. Cation occurs where? Atom next to a lone pair. That's typically called alpha cleavage. That's a general term. But if this is your so-called functional group here, the first carbon is called alpha, the next one's called beta. Alpha cleavage is where you cleave between the alpha and beta. That term is kind of loosely used, but we'll use that term. This is an example of alpha cleavage. What else do we predict here?
I don't know, I didn't put anything else here. Interestingly, the predicted cleavage is not even the base peak. The base peak is actually 31, which is m minus what? M minus 43? 31, I'm not sure what 31 is. Maybe you can think about it, but that's a little bit odd. The base peak is not something that we could predict. It may actually be a granddaughter peak. A lot of times your cleavage peaks are called daughter peaks. They come from the parent peak. What's to say your cleavage peak can't cleave again? It can. That gets very complicated to interpret sometimes. It might have been where your cleavage peak cleaved again. In the end, we're not going to assign that. Okay? Let's look below. Down here we have an amine. Primary amine. Molecular weight is 101. First off, we can say something about that. All of our previous molecular weights were even. If you go back and look at them, they were all even. Now we have one that's odd. Well, that's not just random. There's kind of a nitrogen rule. If you have an odd number of nitrogens, your molecular weight will be odd. Okay? One nitrogen, odd molecular weight. I mean, you can just look at ammonia, NH3. What's the molecular weight? 17. One nitrogen, odd. Hydrazine, which is N2H2. No, it'd be N2H4. What's the molecular weight of this? 32. That's not odd, so the molecular weight's not odd. Actually, even number of nitrogens, even molecular weight. And 0 is considered even. So if there's no nitrogens, like above, it's going to be even. So that's one thing in terms of just kind of some tricks or some tidbits to help you with your numbers and what you expect. So 101. Do we see a 101? It's actually not there. Or it's quite small. If anything there. That means that if this is indeed the compound, and this is, that the molecular ion cleaved before it hit the detector. And what hit the detector was actually a cleavage peak. One main cleavage. See, this is kind of a clean mass spec. It cleaved one. How did it cleave? It looks like if that's it cleaved here. Put cation where? Next to a lone pair. Did we say that 4 minutes ago? Cleave, make a cation where? Yeah. See, here we go. Did it again. It's going to become very predictable. Why? Because we can do resonance and draw a resonance structure. Okay? Hold on. That was from the previous compound, right? Well, that's not, mine's 43. That's actually, what is the mass of this? What is that, 44? 44? This is also the nitrogen rule. All the previous ions we looked at were even or odd. Look at the one above. Thank you. They were all odd. Okay? Up above, even molecular weight, odd cations. When you have an odd number of nitrogens, odd molecular weight, even cations. How could you use the nitrogen rule?
Well, it's very simple. I mean, what if you were a natural products chemist and you isolated a new compound from a sponge that grows off the southern coast of Australia? You've got this new compound, you don't know what it is. You run a mass spec and the mass is 847. What does that tell you about the number of nitrogens? A number of nitrogens in it. So now you know a little bit about your structure, right? In addition to knowing the mass is 847.
Professor, so even though here, if we lose a methyl group, we would have formed a tertiary cation.
You think you're looking for another cation other than this one? Very good. Maybe we can cleave here. Instead of putting cation here, you want to put cation there? Basically what we're doing here is showing predictable or good cations. And if we did that, we would get radical here. So you're proposing that. Well, that's a good cation. Yeah. What's the mass of that? Should be 45, isn't it? 4 carbons is 36, and then there's 9. 45? So this is MZ 45. Is this 44? Well, you do have a little peak at 45. Maybe you did that a little bit. But was it the main cleavage pathway? No, this one was much greater.
It's 56.
You're right, it's not 45 because there's what is it?
They grow up by 14 degrees.
It's 1, 2, 3, 4. 4 times 12 is, that's already 48. 48 and 9 is 57, yeah. 57. Well, let's look at 57. You gotta, it's not even as big as that, okay? So, while it is a theoretically predictable cleavage, apparently the other one was better, because the other one formed a cation next to a lone pair.
So we're looking for the main cation that would be the most safe.
That's your starting point. Starting point is what do I predict? So you predict to form a cation where? Yeah. That's the first type of alpha cleavage. We'll also look to form cations next to pi bonds. Because when we did resonance, how do we stabilize a cation? We either move the lone pair towards it, or we move the pi bond towards it, windshield wipers. Mass spec is all about what cations do you predict, and then seeing if they're there. Maybe at this point we're ready to look back at the mass spec of the 2 alcohols. Remember the very beginning? Now, they're not even isomers, so they have different molecular weights. That one is 60 and one below is 74. This mass spec shows a peak at 60. I assume there's nothing at 74 because it's not shown. The one below has a little tiny peak at 74. So one hit, okay, so that's looking at your molecular ions. Let's also look at how do we expect this to cleave, this top alcohol? We expect it to cleave between which carbons? If that's 1, 2, and 3, between where?
1, 2.
Yeah, that's called alpha beta. Between the alpha and beta carbon to get that radical, what's that cation? Because this cation is next to a lone pair, we can do resonance. Okay? Now, that's not shown. What's the mass of this? Well, that's 29, so it's whatever minus 29. 60 minus 29 is 31. So for that compound, we predict a 31. Do we have a 31? Ding, 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 ding. There it is. Nice and looks like that's that alcohol.
Because the other one, do we predict 31 for the one below? Let's see if we predict 31 down here. Where do you want to cleave at? I'm going to number these 1, 2, 3, and 4. Actually, you can cleave two different sides. If I cleave over here, I can get cation next to lone pair. But I can also cleave over here. That's going that way, and this is going this way. Now we give that cation. Well, these are different. That's one more carbon. This is going to be loss of 29. The original was 74 minus 29 would be 45. This is loss of what? Just 15. So it's 74 minus 15 is 59. Up there we predicted loss. We predicted a peak at 31. Is that right? Down here we don't predict 31 down here. We predict 45 and 59. Well, what do we have down there? I got a nice 45, and the other is 59. Yeah, see I got the two predicted peaks. Now I do have a peak at 31, but it's not as big as up there where we predicted it. You see a little bit better now how, if you use mass spec, you can clearly tell which alcohol is rich. Now, of course, we have structures here. What if you didn't have the structure? How would you approach this? You would look at the numbers. What would be your molecular ion? Pretend you don't have a structure. Which peak is your molecular ion?
6.
Is that the molecular ion? That? Which one's the molecular ion? That? What about that little one there? Or maybe it didn't show up. You got to learn how to recognize what's a molecular ion whenever you don't know what it is. Yeah. Right now we know structure. Question?
Yeah, I think this might be a dumb question, but whenever we're having these rate resonance stabilized cations, I'm not seeing what actually puts it into p orbitals. So this looks like they started all sp3s because we didn't actually have a double bond in there, and the oxygen was sp3 and the carbon was sp3. Normally we have something locking the carbocation into sp3, correct?
What do you mean? Carbocation is sp2.
Sounds familiar.
Carbocation has 3 bonds. Nothing else. 3
right.
regions sp2.
So I think it was okay.
And then the lone pair, anytime a lone pair is next to a p orbital, that's not going to be in a p orbital. So you have 2 p orbitals, and they're conjugating. Okay, now let's move over here. Basically, you have to remember what are the 2 ways we stabilize cations. We move lone pairs towards it. We also move pi bonds towards it. This is a compound with no lone pair, but it has pi bonds. Molecular weight's 120, and I see them 120. Why is that not in the molecular ion, 121? Because we know that we always expect like a little bit of C13, so you get used to seeing what molecular ions look like. This is either in here or it's not shown. Now the base peak is pretty clean mass spectrum. One base peak of 91. What is 91? Well, that's obviously loss of 29. And that's typically an ethyl. Where does it cleave? see, it cleaves here. Because if that's the functional group, that's alpha and beta. If it cleaves between there, it makes that plus your alkyl radical. And that's 91. That's your benzylic cation. Remember the position next to the benzene ring called benzylic? It's a great cation. Resonance stabilized. We showed resonance structures of that. So that's a resonance stabilized benzylic cation. In fact, it's your resonance structure. Now this thing actually rearranges to something else. It's 91. I'm not going to talk about that. If anybody's interested, you can look that up. Rearrangement of the benzylic cation. Okay, compound below is also 120. Isomer. This gives loss of not 29, but loss of 15. Why? Because you expect to cleave here to give that plus a CH3 radical. Loss of 15. This is not 91, but 105, right? Is that 105? How do you make benzylic cation? Why do we not cleave here? I mean, that would also be why do we not make that cation? Not resonance stabilized. Now that'd be a good structural consideration. Why is that not resonance stabilized? Basically because the carbon now has two p orbitals, but all six are like this. The new empty one is perpendicular to that. Okay, it's not part of the pi system. Okay, that's not a good cation. Your benzylic cation is what you want to form, and when you form it down here, you only lose 15, and so down there the base peak is not 91 like above, but 105. So these isomers can easily be distinguished using mass spec.
So that you really can't tell that that one didn't form in the black one, correct?
You can't tell what?
That carbocation didn't form, or that cation didn't form, since it would have been the same as the large peak.
True, but theoretically, we would never predict that. You want to predict the good cation. There's probably plenty of other examples where you could see a difference in the bad and the good. Okay, let's look at carbonyl compounds. Molecular weight 86. We actually have an 86 over here. The main cleavage peak is here, and I've actually already interpreted, given the structure for it, for this cation. With the benzene rings, where do we put cations? We didn't put it on a carbon next to a lone pair, we put it where? We put it on a carbon next to a pi bond. Same thing here. No, it's actually not the same thing here. No, sorry. We're not putting it on the carbon next to a pi bond. We're going back to lone pairs. We have lone pairs here. We're going to cleave to put cation on the atom next to a lone pair. So the lone pairs are there. Where's the atom next to the lone pair? There. We want to put cation there. If we cleave here, we get that plus the propyl radical. So we lost, 45? And so this is, no, we lost what? What is that? Is that 40? Is this 43? So we lost 43, is that right? Okay. We split the mass right in half. Why is this a good cation? Because it's resonance stabilized. This may look odd, a positive on a carbonyl carbon, but it's resonance stabilized. We can move electrons down, and we get, I'm drawing the carbon. Now we have triple bond, one lone pair left, and a plus there. That carbon is sp, and so it's linear. So that's really not a correct bond angle right there. It's really linear. Now I'm showing it linear with the correct bond angle. Which is major resonance structure? Left or right? Marco? Yes, this is major. Why? More bonds. Okay? Even though positive, oxygen is positive, we know as long as we have an octet, oxygen's okay being positive. As an octet. This is called the acylium ion, and acylium ion. When you have the positive that looks like it's on the carbonyl, major resonance structure over there though. Acylium ions are formed in mass spec very commonly because it's resonance stabilized. We'll also see acylium ions in organic tube when we do a certain reaction. Could we get another acylium ion here? Could we cleave at another position? What about over here? If we cleaved over there, that would give that acylium ion plus a methyl radical. Now I could show the major resonance structure, but we'll just leave it at that. What's the mass of this? We lost 15, so it should be 71. Do we have a peak at 71? Ah, I've already drawn it, right there.
So why would that not be more favorable since the sp3 will donate to stabilize that carbocation?
There's no additional. This has sp3 donation, this has sp3 donation. When it's in a chain, it doesn't really matter. Only when it starts branching. But it's still a valid question. Why is the other cleavage so much better? It doesn't have to do with the cation. It actually has to do with the radical. Over here, what was the radical? Did I draw it? I don't think I drew it. It was that, right? Over here, it's just this. Now, even though the radical doesn't show up, it's still being formed, and it's still part of the thermodynamics of the reaction. Occasionally, you can look at the radical and say, well, which radical is most favorable? Methyl radical or this guy? How do we judge radical stability? We know how to judge carbocation stability. Well, radical is the exact same. A radical is electron poor. It does not have an octet. So it's electron poor, just like a cation. And how do you stabilize something that's electron poor? You donate electrons towards it. Why is this more stable than the methyl radical? Because it has these sp3 carbons that donate towards it. Where that carbon doesn't have any sp3 carbons donating towards it. It's the same as if it was a cation. This is a better radical, so it cleaved this way. But you don't see that in the mass spectrum. You only see that portion in the mass spectrum. That make sense? Questions, guys?
So that kind of change does make a difference.
Tall peak, short peak. Let's look below. We didn't mention this up here. McLafferty. McLafferty rearrangement is just a rearrangement of your molecular ion. Well, it's also a cleavage. Because if it just rearranged, it has the same mass. McLafferty is a cleavage with a rearrangement. An important thing about the McLafferty is you eliminate a neutral molecule. So if a radical cation forms a neutral molecule, what will the other species be? It will still be a radical cation. You don't lose the radical and the cation part. You can cleave them and make a radical and a cation. But if this is splits out a neutral, the remainder will still be a radical cation. So, and this is what I showed here, it's still a radical cation. Okay? I'm not going to cover the McLafferty here. I want you to read about it in the textbook, and I think your lab report asked you to discuss the McLafferty rearrangement of your compound lab. I'm just going to look at it there.
Is that heavy to be right in?
Do what?
Is that not too heavy to be of that mass? The only thing that'll show up there is the ion, correct? The cation. Which is,
Yeah, this is the cation. It's a radical cation. Radical cation with a mass of 58. 58. Yeah, that should be 58. Let's look at the one below. What do we predict? Basically, you can cleave on both sides of your carbonyl. If we cleave here, well, let me cleave on the other side because that's what I showed. If we cleave there, we get cation here and radical there. Cation there plus radical. So we lose 29. If we start with 86 and lose 29, that should be, what, 57? That's hopefully 57. What if we cleave on the other side? What do we get? It's the same exact thing. So that's really the only acylium ion that we predict. Okay, what type of questions will we see? How about over here? There's 3 mass specs and there's 3 compounds. Assign each compound to the correct mass spectrum. But I want you to do those on your own and we'll look at them tomorrow. How do you do this? I would start with the structures and say, okay, what type of cleavage peaks do I predict? Once you have all your predicted peaks listed, then look at the mass specs and see which one contains the predicted peaks. If you have 2 that both contain the predicted peaks, maybe you'll need to look at another type of cleavage. For example, Yutong pointed out that it could have cleaved by a tertiary cation. Take a look at that. Let me show you a couple of examples. Very often, mass spec is coupled with gas chromatography. Because a lot of times you have mixtures. For example, you may run the mass spec of blood or an extract of blood. There can be lots of things in there. And if you just send everything as a mixture through the mass spectrum, you're just going to get tons of peaks. And it's going to be just too much to interpret. Because of that, you very often want to separate mixtures first. Gas chromatography will separate things. And after each compound is separated, it's then sent to the mass spec component. And then when you get the mass spec, it's just of a pure compound. So GC mass spec is a dual instrument that's usually always coupled. It's very rare that you actually see a standalone mass spec. Here's an example of GC mass spec. The GC is a chromatograph. It will separate components and give you signals based on retention time on the column. This was a mixture. It turned out to be a mixture we made in the research lab. We were trying to fluorinate compounds. This was the resulting mixture. It was shown to have 4 components. So each component we can then send to the mass spec. And below is the mass spec of each component, labeled A, B, and C. The fourth one is not really, there's no mass spec shown. It could have been. From the mass spec in the molecular ions, we can see that this has 293, 255, 237. This ended up being starting material. We were doing a fluorination reaction. One fluorine was incorporated because the mass went up by 18. Replace the H with an F. Here, 2 Fs were incorporated. The mass went up by 36. But you see, the GC also tells you the ratio, and this is a much taller peak. It's predominantly starting material. Only a small amount of the original was fluorinated. The original reaction is shown below. This is the power of GC mass spec. Components, and then you can sort of identify. On the back is an example of a pure compound where when you do the GC, it's just one peak. It's pure. Or it ended up being pure. Confirmation of purity. And the molecular weight is 337. And we see a nice, actually tall molecular ion over here to confirm that it's indeed 337. You can try to interpret these, but very often the first thing you're looking for is just your molecular ion to confirm it doesn't have the right mass. Okay, let's take a 3-minute break, and then we're going to move to the new handout. After the break, we'll see if there's any questions about what we've covered.
She didn't come to class. You didn't do it like I suggested. I suggested you turn this and then add things in plan. I have to look closer at that. That's not the way I do it. Apparently you got it wrong.
Right.
I would turn it first and then add the things up or down.
I'm just curious for this.
I'm not showing you specifically where the charge is. I'm showing you that, like, it's shown right here. Okay. I'm not showing you where the charge is. That's a generic way to show charge. It's how they show charge in Chem. It's not H. They just say this is the thing probably don't say why I don't
So this entire thing is all. So that's something attached to the other H.
what is attached to it.
This looking like, I don't see, this looks like something, and then this looks like something.
It's a molecule that has a single electron somewhere and a positive charge. That's I mean, in Gen Chem, don't y'all show anions like this? Or don't you show anions? You never seen it shown like that? I thought that's how y'all did in Gen Chem.
An AI shown like, Okay.
Bracket up there?
No, okay, so that's a bracket. Okay,
It's a bracket.
sorry, that's, for some reason.
That's how they do it in Gentile. I hate that, but that's why I'm doing it here, because I don't know where the minus is.
Okay,
It's like they don't know where the minus is in Gentile. I mean, if you draw the Lewis structure out, minus is on oxygen. It's actually,
okay. It's also this, okay, the bracket is the shape of the group that was also removed. The, that's what it was. That was actually like the propyl group that was removed.
I understand now.
Are the handouts from today somewhere?
Well, that's 29, that looks like a couple. Apparently, when Cleve put some of the patterns. It's not ridiculous. Apparently, it is.
Okay, guys. Moving on to substitution elimination reaction. Major topic. It's largely our last major topic, of course. It's a very big topic. Substitution is our first, and we'll move to elimination.
There'll be another handout.
Here in the synthesis of Allegra, we see, partially through the synthesis, a substitution reaction right here called SN2. We'll learn what that means, substitution by a nucleophile bimolecular. This OMS, that's a mesylate. That's sort of rare. We'll see a tosylate will be more common to us. On that carbon, they reacted with this amine, and then the amine is what's reacting. The amine nitrogen replaces the oxygen. It substitutes for it. And when we're doing alkene reactions, were we doing substitution reactions? What were we doing with alkenes? Addition. We have an alkene, we add H and Br. Adding. We're not replacing anything. Substitution is like replacing. And that's an example there. Synthesis of Allegra. By the way, also, the next step includes hydration of an alkyne. The alkyne gets hydrated to the ketone using the mercury. Y'all did not use mercury in lab, though, did you? Okay, on the next page, mechanisms. You can use this as practice in addition to the workbook. Lots of different mechanisms. They're all substitutions. But we need to have our mechanistic thought. Here, the OH is substituted with a bromine. Okay? Down below, we have a cyclization reaction where instead of a chlorine on this carbon, the oxygen is now bonded to the carbon. And we made, you can see which bond we just made. We just made that bond right there. Used to be a chlorine bonded there, now the oxygen is bonded there, but the oxygen is also bonded back around, so you got a ring. Basically all substitution reactions. We're in chapter 7 and 13, textbook. The title, nucleophilic substitution. At what type of carbon? Tetrahedral carbon, which is a saturated carbon with 4 bonds, right? You don't do this chemistry at an sp2 carbon, alkene carbon. Okay, there you go. General line reaction for substitution. Some type of carbon framework, it's organic chemistry with a leaving group. We've mentioned that before. What does a leaving group do? It leaves. Takes electrons with it. Most common leaving groups are your halogens, with iodine being your best one. Like a bromine. We saw bromine be a leaving group when we did the bromonium ion, and something came in and kicked off the bromine, opened up the bromonium. The bromine was a leaving group. You're going to react this with a nucleophile, something that likes positive charges. So it itself has high electron density, typically a lone pair. Nucleophile almost always has a lone pair. In the line reaction, the nucleophile replaces the leaving group. So the nucleophile is now bonded, the leaving group is left. The leaving group will take on a lone pair. It may be minus, it may not be. Very general, no charges are shown there. Specific example down here. Leaving group could be bromine, the nucleophile could be hydroxide. Hydroxide replaces the bromine, and we get Br minus form. You say it replaces it, or it displaces it, or it substitutes it. So that's a substitution reaction. There's 2 main substitution mechanisms, though. One's going to be called SN1, one's going to be called SN2. What is the mechanism here for this model reaction? We're going to show both mechanisms, SN1 and SN2. We're going to show it 2 different ways. Then we're going to look at the 2 ways and ask which is better. Which do we like better? Okay, how could this happen? What do you want to do first? Just someone tell me, we'll talk about it. Is it just magic? No, we're going to do more than just say it's magic. How's this going to happen? Taylor? How's this going to happen? What do you want to propose? What needs to happen? Oxygen needs to be bonded there and bromine needs to not be bonded. Okay, how are we going to do this? What do you need, Utah?
Oh, sorry, worksheet. Can I have one of the worksheets, please?
This handout?
Yes.
Okay. That's what needs to happen. How's it going to happen? What do you want to propose?
A lone pair attacks the partial positive of the carbon bond to the bromine. And then
Okay, so you're saying there's some partial positive here, because there's a dipole there. I agree, there is. Yeah, it's good to know. Since that's partial positive, What's over here? Negative. Are these going to be attracted to each other? Yeah, positive like negatives, right?
But for SN1, doesn't the algae leave first?
Oh, you've been doing some reading though. I was just going to do it, okay. Yeah, since I already called this SN1 there, let me do it the SN1 way so we have that here. Okay, bromine's got to leave. Everybody agree? Well, let's just make it leave. That is, the bromine's bonded to the carbon. Let's say the bromine just, okay, I'm bonded to the carbon. All right? See you later. I'm going. But I'm taking my electrons with me. Pretend I'm taking the whole stuff. I took it with me. See you later. Okay? So the bromine just takes the electrons and takes the height. What would that give? If that happened, that would give that, how many H's there? 2, and that's it. So what is that? A plus charge plus what?
Beyond
Br minus. That's what the bromine just, what do we call that?
Bromine.
Ionized? We do need to form Br minus. There we go. Now what could we do? Now these electrons can do what? Add here. And if they make a bond there, what do we get? We get now have both products. Oxygen makes bond to the carbocation. There's a mechanism.
Under what conditions would the algae just leave?
Let's talk about it. How many steps in this mechanism did I show?
2.
What do you want to call the first one? Ionization? What do you want to call this one? It may take more than one word. Nucleophilic addition to carbocation. I mean, that's more than one word. I don't know how to say it in one word. You could call it addition. I hate just calling it addition because it sounds like it's an addition reaction. Overall, it's a substitution reaction. There's a two-step mechanism. Do you like it? Do you not like it? What's good or bad about it?
Why
Any
does
questions about it?
Why does the halogen just leave?
Why the what, where?
Why does the halogen just leave?
Why does it just leave? Can a halogen just leave? What happens if you put HBr in water? What happens? It ionizes? What's the mechanism? It just leaves and you make H plus, Br minus? It's actually a little faulty, that's really not true there.
So then the H2O take the H?
Because really it's water taking the H, right? But we do say it's ionizes. So that's the example. If you don't include the reality, Br just ionizes. Well, this is just Br ionizing from a carbon. What type of cation did we make? Primary. What do you know about primary cations? They ain't good. Okay? So my mechanism shows a cation that ain't good. So is this a good mechanism? No. Well, what I just showed is an SN1. An SN1 involves a carbocation intermediate from ionization. Plenty of SN1 reactions take place, but usually when an SN1 takes place, the leaving group is on a tertiary carbon, because a tertiary cation is best. So, let's move down to the next. What's another way to show this? Well, SN2. Well, what is SN2? What's another way to show it? How can we get the same products but do it a different way? Can I raise here? Questions?
Water.
Well, back to what was mentioned earlier, there's a partial positive here. What's another way to do this? Another way to do this is this not to ionize because it doesn't want to ionize. It doesn't want to make a carbocation. Instead, these electrons can come in here and push it off. What if that happened? What would those, that's two arrows concerted together. What would that arrow movement give? Okay, what does this arrow mean here too? Electrons leaving and moving on to bromine. What does that arrow movement give there? Chase? Shelby?
Which arrow, the arrow going from
No, all that. What does all that arrow movement give?
oh, it gives,
There you go. It gives that. Because what does this arrow give? Bond to carbon. And what is that? Electrons leaving. There. There's another mechanism. Is that the same as the above method they did? No, the above had a carbocation form. How many intermediates down here? There's a different mechanism. Which mechanism do you like better? Well, since the first one had a primary cation, I say it's bad. Obviously, the second one. What do you not like about this one down here? Any questions about it? Why it's feasible? Anything you don't like about this mechanism? Why would hydroxide attack that carbon? Partial positive. It's not a full positive, but it's partial positive. And this indeed is known to happen. Okay? We don't always have to attack a carbocation. We sometimes can attack a tetrahedral carbon that has a leaving group, and we can push that leaving group off. When did we do this before? Remember bromonium ion? Something like water? What did this do? It attacked there and pushed that bromine off? Now that was a strained ring, and the bromine was positive. So there was other reasons to want to do this. Well, guess what? This is probably going to take a little heat. This is not going to be as easy. This is much easier. Open up that strained ring. It wants to be opened up. Now, this is probably going to require a little heat. Give it a little energy. It's got some activation energy you need to overcome. It's going to be an SN2 called substitution. Let's go back up top. Let's do a reaction coordinate diagram. You still have the reaction on there. For up top, reaction coordinate diagram, we start with this. We end up with the alcohol. Is the alcohol higher or lower? Hard to say. We're not going for, it's still the same types of bonds. I'm going to make it just the same. How many intermediates in the top root mechanism? And it was charged, right? So where do you want to put it? Kind of high? And now we can do our reaction. Activation energy, leading to an energy well. And then when we fall downhill, it doesn't take much energy. That should actually be a little higher probably. This doesn't take much, does it? Doesn't take much to fall downhill. Which step is rate determining in our first mechanism we showed? That one, this is fast. So ionization is the rate determining step. Nucleophilic addition to the cation would be fast. Yeah, this is the first mechanism, right? Question. Of the two substrates, the two reactants, how many are involved in the rate determining step over here? Look at your first step that we showed for the above mechanism. How many of the reactants were involved in it?
One.
Which one was it, Amanda? The alkyl bromide. That's why it's called an SN1. Substitution by a nucleophile, unimolecular. Uni meaning one. Only one thing involved in the rate determining step. Okay, SN1. Now let's look at this mechanism. Let's do a reaction coordinate diagram. what would it look like? How many intermediates down here? None. You're just going from here to here with a transition state. I mean, these two are like going from here to here with a transition state. The transition state is just going to look like this.
So, since it is an actual reaction that's going on here, you're not isolating the two things, would we include the OH minus and the Br minus on the reaction coordinate diagram as well? And wouldn't we look at, I guess, Br minus as being more stable anion than OH minus because of the size? And then kind of have the second part having a lower energy state? Or is that too much assumption?
You could, I'm just not getting that precise about it. I'm just showing the main organic reaction. Main organics. How many intermediates in this reaction? None. Okay. Which is the rate determining step in this reaction? Which one? Which step is the rate determining step?
It all has to be one step.
The first.
Transition state.
The first one.
And the last.
There's only one step, right? So that better be the rate determining step. Right? Does the rate determining, how many molecules, how many of the reactants are involved in the rate determining step?
Two.
Two. There's only one step. They're both involved. That's why it's called SN2. I showed you an SN1 and SN2. The model reaction is indeed SN2. Why? Because you don't ever want to form a primary carbocation. It goes the other way around. Okay? The nucleophile adds and leaving group leaves. Kinetic studies. Kinetic studies would tell us that it's SN2. Because the kinetic studies have shown, I'm reading, that the rate of the example reaction can be affected by changing the concentration of either the alkyl bromide or the hydroxide. You change either one, you change the rate. What does that tell you about their involvement in the rate determining step? They're both involved. If only the alkyl bromide was involved, it wouldn't matter what you do to the hydroxide concentration, it doesn't affect it. The information tells you they're both involved. That information tells you that the mechanism is thus SN2. See, that information tells you it's SN2. We can also write a rate equation. The rate for this reaction is SN2. They're both involved. We write that as some type of constant for the given reaction. But it's also times the concentration of both reactants because they're both involved in the rate determining step. If it was SN1, it would just be constant times which one? Just that. Because that's not in the rate determining step. Question?
Will the SN1 substitution, will it always get the primary carbocation?
SN1 will always get the
Will you always have a primary carbocation?
No, you'll never have a primary carbocation. Never do primary carbocation. I showed you that way, but I'm telling you that ain't the way that happens here. The way that happens here is SN2. I showed you two different ways and then we evaluated it. And we see that the SN2 is much better. That doesn't mean we won't do SN1. We'll do SN1 when the leaving group is on what type of carbon?
Tertiary.
Tertiary, yes. Sometimes secondary, never primary. Guess what? We're going to state that on the next page or two. Okay? Okay, let's look at some stereochemistry here. What if we add stereochemistry and make it R here, reactions with KOH, we get these two products over here. Looks like a substitution. Is it SN1 or SN2?
SN2.
do you know it's SN2?
You
Because
know the R,
the stereochemistry is up.
Well, look at the outcome. This is R. When the hydroxide replaced it, it's now gives S. That is, the bromine is going back, but now the new thing is going front. And indeed, it's inversion, R to S. And you only get S. That is, this reaction is enantioselective. You only get that enantiomer. Br minus, with the K just being spectator, okay? Let's get rid of that, right? That's minus, and this is minus. Spectator ion. Complete inversion. This is SN2. Why? Because if it was SN1, what would the stereochemical outcome be? Let's do SN1. What's SN1? What's the first step?
Bromine leaves.
Okay, if that leaves, we get that cation. Now, if hydroxide now attacks, is it going to be attacked in the front or back? Either. It'll be racemic. SN1 gives racemic, because we know how you attack a cation from either side. We didn't get racemic, we only got S. That means it's SN2. Why does it mean it's SN2? Well, the fact that it's SN2 means that these electrons come in and kick that off at the same time. It's concerted. But how do we know whenever we kick something off, how does the new thing come in? Backside. We did this, that's why we talked about this earlier. Now, what's backside? If the backbone is in the board, maybe we can just build molecules since I got them right here. Backbone is in the board. Actually, eclipse there. The bromine, we'll call it red, is back. Well, now it's back. Uh-oh, well, now it's up. The only way I'm going to get it back is to make the other, disconnect. Okay. There it is. Everybody agree that's the molecule? Bromine going back? Okay. Now how does the hydroxide come in? Does it come in over here? No. It comes in behind the bromine, comes here. Okay. Hydroxide's green. Okay. Okay, come in backside. Oh, you want to come in over here. How about this? No, backside is right behind the bromine. So you're going to bond there. We're going to kick this off. But what happens here is this has to sort of move. And it does that when it comes in. That was with the bromine. This H, or whatever is there, has to be moved back. Remember when we did that before? It gets pushed that way to make room for this. But now the OH is forward. That's what we're showing here. See, the H is forward. But with that, she pushed that in, that H has to move back, and now it's back. That's all with inversion. But that's why the OH is forward. That stereochemical outcome proves it's SN2. Because if it was SN1, we would have gotten racemic. Take home, whenever you do SN2, you get inversion. Now, if it's not chiral, it really doesn't matter. But it still comes in backside. Just maybe the carbon where the chemistry took place is not chiral, so there's only one way to show it anyway. Okay, question here. Is an SN1 mechanism more or less likely for this reaction compared to the previous reaction? Well, that's secondary. So it's more likely. So secondary is better than primary, but we know from the stereochemistry that it still was SN2. Stereochemistry outcome is used to determine mechanism. The answer is it supports SN2. The experimental evidence is the stereochemistry I told you. Fire-house inversion obtained. We just showed it. So let's show it on the board. Because we want to show it, be able to show it on paper and also some other details about it. Thought I added this in. Now, I have to think about how to draw this so we can see it. I want the bromine in the plane. The carbon has an ethyl and a methyl. Let's do this. There's a methyl and there's an ethyl. And then there's also an H on that carbon over here. There's also an H there, yeah? If that's R, is this R? No, that's actually S. I'm going to have to make that the ethyl because with the H going away, bromine's here at 6 o'clock, ethyl is 9 o'clock. That's R. Okay, that's R. That's just that compound up there redrawn with the bromine in the plane. Now how does the hydroxide come in? If the bromine is there, hydroxide comes in over here, opposite. So hydroxide comes in over here. And as it comes in, this bond breaks. And that's the transition state. But let's draw the transition state. Okay? Sometimes transition states are put in brackets. What's it going to look like? We have a carbon. And this bond is forming. And as that's forming, what's happened to the Br bond? It's breaking, and so we can sort of show like this. Now as this is minus here, but as it starts bonding, what's this charge becoming? It's not fully bonded. Once it's fully bonded, it becomes neutral. But what is it as it's partially bonded? Partial minus. Now the bromine's neutral, but as it breaks, it ultimately becomes minus, but as it's breaking, what is it? Yeah, for a net of minus. See, the net charge is minus. This is your transition state, or sometimes called the activated complex. Importantly, let's come back. Let's draw this at the end. We're about out of time here. What do we ultimately get to? Ultimately, this bond fully forms and this fully ruptures. And we end up with the OH over here fully formed. But now, this is like this. Let me make that a little bit more like that. And this is like this. And this is like this. Plus what? Br minus. Okay. What we have here is inversion. And let's look at this to finish up here. Here, pretend over here, this is the bond to bromine. When that's a bond to bromine, same things over there. Bond to bromine here. The other three things are sort of that way a little bit. You see how they're kind of that way a little bit? Let's do it like this. Pretend that's the ethyl, the methyl on the H, bromine this way. When that OH comes in, what happens to these groups? They actually flatten up. And that's how this is supposed to be eclipsed. They're right in front of each other. Now, as the bond fully breaks, what happens? these things come this way. And that's your inversion. Because if you look at it, this is R, but over here this is S. Now the alpha is still forward, but it's forward. When this comes in, what does the alpha have to do? It first flattens up, right in the middle of the transition state, but then it is pushed back. And that's like what we had right here. When you make the bond, you go forward, and then ultimately you push it back when it comes in. So that's a look at it. Transition state, importantly, last thing here is, what's the geometry here? It's like you got something straight here and then straight. What is that geometry? Trigonal planar. Okay? It's like everything is forward, then it comes planar. The bond angles of what? See, it's straight up, and I got two. Pretend I got one straight down. And then I got two like this. But that's trigonal planar. Straight up, straight down. Bond angles of what? 120 degrees. Now, usually an sp2 has what left over? P orbital. And the p orbital is perpendicular to the plane. If that's the plane, this almost looks like a p orbital. In the end, your transition state is sp2-like. Bond angles are important. What bond angles have to be achieved in the transition state? 120. What if the molecule can't achieve 120? So I have a tough time doing this mechanism. There's a couple of questions in the workbook about that. Remember your transition state? That's how the inversion takes place. Everything, okay? See you tomorrow, guys. We may have a quiz on stuff up before we started substitution. Resonance, dynes, mass spec.